Hi, how you doing? I want to talk to you about hyperbolic functions, okay? These have got a lot of applications in the real world in mathematics, okay? It's important that you know what they are. First of all, you notice anything different? No, I'm not talking about that. So I'm in a hat mood today. Kind of feels like I'm at the beach. So, yeah. No, Lord Vader, look what he's wearing, okay? Now, it looks like a chain, it's actually a shoelace, okay? But yeah, it's actually a shoelace, okay? He actually is wearing a chain there because it's what he uses to keep his cape on, okay? So if you look close in the movies, he's wearing a chain. Okay, I'll come back to that later if I remember. But yeah, this could either be a hanging thread, or it could be a hanging rope, piece of string, could be a chain, okay? But look at the shape that it's making, okay? If it's just left to hang like that, with gravity only acting on it, okay? Notice the fundamental shape is always the same, isn't it? Okay? That's very important, okay, in mathematics, okay? Because there are a lot of instances where there are this sort of shape just hanging around, okay? Just try and think of them, okay? Think of where you might have seen these. It might be on a necklace that someone's wearing, okay? The power cables, look at the power cables next time you're out, okay? All those hanging wires there, they're put in the same shape. Christmas decorations, when you put up decorations, you just hang one end on the ceiling, the other end on the ceiling as well, okay? All sorts of places, okay? Barriers, okay? When you have a barrier and you've got two bollards and you've got a chain that's hanging between them, okay? All over the place, okay? These are what we call catenaries, okay? It's called a catenary. Let me just spell that word out for you, okay? It comes from the Latin word, which means chain, okay? It's called a catenary, okay? Like I said, it looks like this, okay? A question that you might ponder later on is it the same as a parabola? It looks very similar, doesn't it? And that's the thing, it looks very similar, but it's not. It's not the same as a parabola at all, okay? The catenary has got a particular equation. You know, the parabola has got y equals x squared, it's a simple equation. The catenary has got this equation, y is equal to that, okay? It's called the hyperbolic cosine of x, okay? Hyperbolic, that's why the h is there, okay? We say coshx, okay? Coshx, okay? And that's what, you know, the curve actually is. We can define it further using exponentials, okay? As this, 1/2 of e to the x plus e to the negative x, like that, okay? Maybe you just pause the video now and you sketch that graph, okay? You know what e to the x looks like, you know what e to the negative x looks like, add them together, half it. Obviously, you want to get something like that, but where's the y-intercept, okay? Is there an x-intercept? Maybe you want to work out what those are, okay? So maybe just pause the video and have a go at it. Done? Good. Well, when you do it, it should look like this, okay? There we are, like that. And the y-intercept is 1, okay? And that is the graph of y equals coshx, okay? Some interesting properties. It's symmetrical about the y-axis. Does mine look symmetrical? Good enough, okay? Good enough, okay? Because it's symmetrical about the y-axis, okay, you could say cosh of negative x is the same as cosh of positive x. It's got similar properties to the trigonometric cosine as well, you see. Same with trigonometry, isn't it? Cos negative x is cos positive x, okay? And we might just come back to that a little later on. So that's one of them, okay? Your next question might be, is there a hyperbolic sine and a hyperbolic tangent? Yes, there are. Okay, yes there are. So let me just rub this off. Okay, let's just talk about that. Incidentally, this is the most interesting one because it's got its own name for it, catenary. The other ones are just called hyperbolic sine, hyperbolic tangent. Okay. But they do have applications in the real world as well, just not as many really. Most of them are just when you're solving equations and stuff. Okay. So next, why don't we just mention the hyperbolic sine, okay? So it's written like this, okay? S-I-N-H. Now, how do we say that? Well, depending on how you've been brought up in mathematics, you could say it a number of ways, okay? I say shine, okay? Some people say cinch. I hate that, because it's got the word sin in it. Some people say cinch. It's up to you, okay? I prefer shine. So I'm going to call it y equals sinhx. Okay? The way this is defined is as follows. y equals a half e to the x subtract e to the negative x. Notice how similar that is to cosh. Y equals coshx, remember, was half e to the x plus e to the negative x. Shine is y equals half e to the x subtract e to the negative x. Why don't you pause the video and try and see if you can sketch it. Again, you know what those graphs look like. Just do this, subtract this, and then halve it. I'm not going to give you a clue this time. I told you about the chain. Okay, so you knew what you're looking for. Just give it a few minutes. Done? Okay. What graph did it resemble? Where have you seen something like this before? See, if I was to just draw that out, you might think, oh, it's the graph of y equals x cubed. It's similar, isn't it? But again, it's not the same. I'm hoping you can see it's not the same because y equals x cubed is not at all like that, is it? Yeah. But that's what the graph of shine x looks like. Okay, like this. This one is a one-to-one function. Okay, and you can see when x is 0, y is 0 as well. You can easily substitute that in. You see, e to 0 subtract e to 0, 1 subtract 1, 0. Okay. Here, this one's got an interesting property, like the trigonometric sign. That is, shine of negative x is equal to negative shine of x. Okay. What that means is that you can rotate this graph around the origin, pi radians, 180 degrees. Okay, and you get the same thing. Incidentally, now that I mentioned angles, these are not angular functions. Okay, trigonometry are angular functions. Okay, you put an angle into it and work out the sine, cosine, over tangent. These are not angular. Okay, so you're not doing shine of x degrees or whatever. Okay, so just something to bear that in mind, because trigonometry, they're circular functions. Okay, based on the circle. Okay, obviously they're circular functions. So I don't know why I said that. These ones, okay, these are based on what's called the hyperbola. Okay, the hyperbola is a different sort of curve. Maybe that's something you research separately, but I'm not going to go on to. I'm not going to go off on a tangent. Yeah. Right, so that's that one, and then lastly, you can know what's coming up. But how do you say it? Well, I'm rubbing off this board. You might want to think about how do you say the hyperbolic tan. You might know how to spell it. Okay, so you can see what you do is you write out sine, cos, tan, and then just put h on the end for hyperbolic. Okay, yeah. So how do you say it? Right, I say tanhx. Some people say than. Okay, it depends what you prefer, really, and what you slip into. It also depends on what your lecturers will do. To be honest, you know, at university, you know, if they all start saying than, they might insist that you do the same, or it might just rub off on you. Anyway, I say tanhx. Okay. Well, how do you define this one? Okay, you're going to find there are a lot of similarities between hyperbolic functions and circular functions. Why is that, do you think? Well, it's because they're all cut from a cone, you see. That's probably a separate video I need to do, isn't it? Okay, they're called conic sections. Okay, if you take a cone, which is obviously a 3D shape, if you slice a cone using a plane in different ways, if you slice it one way, you're going to get a circle, slice it another way, you get an ellipse, slice it another way, you get a parabola, slice it another way, you get hyperbola. And that's why there's some similarities. Okay, it's shine over cosh, like tan is sine over cos. Okay, so what does that mean? It means you could probably pause the video and work out what it is in terms of e to the x. What are you doing? So shine x over cosh x. Well, the halves are going to cancel, aren't they? Half divided by half. So you've got shine, which is going to be e to the x subtract e to the negative x, and on the bottom e to the x plus e to the negative x. There. It's just that that's probably not the best way of writing it. You can simplify that a little bit. How do you simplify that? Just multiply top and bottom by e to the x. So you get e to the 2x, subtract 1 over e to the 2x plus 1. Okay, that's helpful for sketching our graph. Okay, so you can write it like this. Okay, or alternatively, you can write it like this. Okay, if you took this and divided top and bottom by e to the x this time, or multiply top, multiply e to the negative x, you'd get y equals 1 subtract e to the negative 2x over 1 plus e to the negative 2x. Okay, all three are the same thing. Let's put y to make it tidier. Okay, maybe just sketch the graph and see how you get on. Right, now because I've used up all my board space on that, I'll just do the graph here, shall I? So I'm just going to put some axes there, just ready to go. Okay. Incidentally, this is a one-to-one function as well. Okay. And what's it going to look like? Okay. Well, when x is 0, y is 0. Okay. I mean, you can see that from this. You know that when x is 0, sin x is 0, and coshx is never 0. So 0 over 0. So it's, you know, it's just going to cross through there. Okay. What about the rest of the graph? Okay. Asymptotes. Remember when you've got equations and you've got fractions involved? Let's see if they're in asymptotes. Okay. Let's see if there are any values that y cannot be. Okay. Or let's see what the range of values is going to be. Okay. The thing to do is let x tend towards infinity. If you look at this bottom one here, because it's a better one, okay, as x tends towards infinity here, what does y tend towards? You've got to be quick, okay? So that's 0, so 1 over 1. Y tends towards 1. Okay. So what that means is there is an asymptote here at y equals 1. And you can check, but the graph will never be above y equals 1 either. Okay. Check it if you want, but it won't. Okay. So what's the minimum value? Okay. What I'm going to do is I'm going to use this equation here. I'm going to say what happens when x tends towards negative infinity. Because what I've done is I've said, okay, as the graph tends towards infinity, I know it's going to approach that line, but what happens when x tends towards negative infinity? What's it going to approach? You can probably guess. Okay. Let's just put it in. So x tends towards negative infinity, that is 0 and that is 0. Negative 1 over 1 is negative 1. So y tends towards negative 1. There we go. So there you have it. Okay. That's enough for us to deduce. It's a terrible word, I hate the word deduce, but it's correct. To deduce what the curve looks like. If it passes through the origin and it tends towards this curve here, it can't do that. It doesn't curve upwards because that implies it's going to cross it, okay? So it does this, okay? See that? And then it's going to do this on the other side. There. It's kind of a lovely function, isn't it? Okay. See that a bit closer? Yeah, okay. Yeah, as I said, it's a one-to-one function as well, and it's a function because it's defined for all values. All these are functions, by the way, because they're defined for all values of x. Okay. So yeah, so that's what the hyperbolic functions are. Okay. Maybe you just have them noted somewhere what sinhx, what coshx, and what tanhx actually are, and yeah, knowing the graph's quite important. Okay. Yeah.